Hello, my name is Dustin and I'm one of the team members here at Filtration. In this video, we will be discussing the 4 types of multi-pass testing that are used to measure the beta ratio and dirt holding capacity for hydraulic and lubrication filters. The 4 tests we will be discussing include ISO 16889, which is the industry standard test, ISO CD 23369 cyclic flow test, which is proposed to replace the current industry standard test, the cyclic stabilization test, and HyPro's dynamic filter efficiency test. Stick around to the end of the video for comparison of the most important advantages and disadvantages of each of these tests. Let's go ahead and get started. ISO 16889 is the industry standard test for hydraulic and lubrication filters. Its main purpose is to detail the necessary aspects of design and construction of test stands, their application of contaminants, as well as the procedures used during testing. Here are some highlights of those aspects. A steady flow rate must be chosen by the operator and measured in liters per minute. The use of ISO medium test dust must be used in one of 3 gravimetric level conditions, either 3 mg, 10 mg, or 15 mg per liter, and continuously injected into the filter test system reservoir. There must be automatic particle counters calibrated in accordance with ISO 11171 in use upstream and downstream of the test element, with counts being taken every 60 seconds throughout testing. Testing will conclude once the test filter's terminal differential pressure has been met. All results must be recorded. Some important things to know about ISO 16889. It is the simplest test to operate and is ideal for laboratory testing and repeatability. Because of this test is the furthest from being a real-world example of how most hydraulic and lubrication filters interact with contamination. Also, due to its steady flow rate, the test offers no view on how flow rate fluctuation can impact filter performance. The next test we will be discussing is ISO CD 23369. This test is the proposed replacement for the previous ISO 16889 because it includes updates and revisions that brings it one step closer to being a real-world applicable test. Some of those updates and revisions are the use of cyclic flow rates in a 4:1 ratio, alternating every 5 seconds of testing, and are measured in liters per minute. The use of ISO fine test dust in one of the 3 familiar gravimetric level conditions. The same standard and location of automatic particle counters are required, but the time between readings may be decreased to every 30 seconds at the discretion of the operator, resulting in the opportunity for twice as much data than the previous test. Testing will conclude once the test filter's terminal differential pressure has been met during the maximum test flow rate. Some other important things to know about ISO CD 23369 are, even though this test is one step closer to a real-world example of filter performance, it does miss important data during testing events, such as flow transition, due to infrequent particle counting. Unlike its predecessor, this test does not deliver 100% of contaminants and flow across the test element at all times due to the method in which the flow rate is changed. The flow rate for this test is changed by the opening and closing of a ball valve attached to a bypass line. When the flow rate drops to the test element, so does the number of contaminants, because the flow is diverted around the test element. Results from this test are also a problem because the data provided is normalized and averaged, not specific, which can paint a misleading image of a filter performance. The next test we will be discussing is the cyclic stabilization test, or CST. CST is very similar to ISO CD 23369 in that it also uses cyclic flow rates in a 4:1 ratio. It utilizes ISO fine test dust and changes flow rates every 5 seconds as well. So let's take a look at what makes it different. CST has a non-constant contaminant feed and utilizes an on and off method of contaminant injection, which means contaminants are injected and then the system is stabilized by allowing the test filter to clean up those contaminants. Then more contaminants are injected. More notable differences are when particle counting is started, how often counts are taken, and which particles are actually monitored. Particle counting starts at 80% of the test element's terminal differential pressure, and the frequency in which counting will be conducted is the operator's choice. Counting may take place either every 30 or 60 seconds. When it comes to particles monitored, for this test, only 5 micron and 6 micron are monitored, and the 4 micron particle size is ignored. Some other important things to remember about cyclic stabilization testing is that by omitting the first 80% of the filter's life and averaging the beta ratio, test results will appear better than they actually are. Also, this test uses the same method of flow rate change as ISO CD 23369, which means that the test element is not receiving 100% of the contaminants during the entire duration of testing. The final test we will be discussing is Hypro's Dynamic Filter Efficiency Test, or DFE for short. DFE testing predates the proposed ISO 23369 test and is a constant contaminant feed process that utilizes ISO medium test dust. This test uses a unique style of cyclic flow with a 2:1 flow rate ratio and cycles lasting 120 seconds, with 60 seconds of high flow and 60 seconds of low flow. The list of things that make this test different from the others starts and ends with data. Hypro's DFE testing produces more useful data than all other testing methods combined by using rapid scanning technology that counts particles every 5 seconds of testing. This level of counting creates data such as overall average beta ratio, transitional beta ratio, and both high and low pressure beta ratio. And in addition to this data, Hypro also includes an end-of-life restart test that cannot be found in any other forms of testing. End-of-life restart testing occurs once the element has captured enough contaminants to reach approximately 90% of the terminal differential pressure. The main flow drops to zero and the injection system is turned off for a short period to allow settling in the system. Next, the main flow is accelerated to the element's maximum flow rate, and the retention efficiency of the contaminant-loaded element is measured and documented. The dynamic duty cycle is repeated to further monitor the retention efficiency of the filter element after restart. This part of testing is what makes Hypro's DFE testing some of the most relevant testing in the industry, with a mimicking of worst-case real-world scenario. Hypro is able to provide an in-depth analysis on what could potentially happen inside our customer systems, and therefore stop issues before they happen. Now that we've discussed the 4 main types of multi-pass testing, let's go ahead and review by comparing some of the most important advantages and disadvantages associated with each of these tests. For the industry standard ISO 16889, the advantages include a simple to operate and less costly investment form of testing, and disadvantages include lack of cyclic flow, making this test the furthest from being a real-world applicable test. For the proposed standard test ISO CD 23369, the advantages include cyclic flow rate, which is one step closer to being a real-world applicable test, and disadvantages include infrequent particle counting that misses important events and data that is normalized or otherwise lacking in the concern of transitional flow. For the cyclic stabilization testing, the advantages include a cyclic flow rate that is also one step closer to real-world testing, and the disadvantages are infrequent particle counts and missed data, data that is normalized or otherwise missing related to transitional flow. It ignores the first 80% of a filter's life, which is unrealistic and takes the test one step further away from real-world applicable testing, and there is no end-of-life restart testing to provide terminal differential particulate retention. For Hypro's Dynamic Filter Efficiency Test, the advantages include dynamic flow rate changes, which makes this test the closest to being real-world applicable. It considers the entire life of the filter being tested, frequently providing particle counting every 5 seconds during the entirety of testing, which provides the most detailed data for every transitional point during, and an end-of-life restart test, which is the only one in its kind of the industry, and provides important data based on the actual worst-case real-world scenario. Disadvantages include that it is not a current standard. This has been a brief review of multi-pass testing. We hope that you have found this content helpful. If you have any questions, comments, or would like more information on this topic or any others, then please reach out to us here at info@hyprofiltration.com.